Okay, I'm Kurt Koitzer, and I'd like to thank Jim for another opportunity to talk to this class. I'll be talking about architecting parallel software with patterns today. I think this is one group that I don't have to motivate the challenge of parallelism. The only thing I'd like to accentuate in this slide is that we have a lot of varieties of parallelism, and I think although kind of multi-core and modest levels of parallelism are kind of holding the day today, we'll see more and more fine-grained mini-core parallelism in the future. So we want to talk about how do we write parallel software, and I'd like to start with what doesn't work particularly well. So I'm saying this is not how to develop parallel code. The style of you take your code, you run it through a profiler, you do the performance profile. If it's not fast enough, you go back to your office or cubicle, scratch your head a while. Okay, recode it with more threads, profile it, go through. And this may seem like a straw man, like one of those things academics love to say, let me set this up so I can knock it down. But the fact is, if you buy a bunch of hardware from a bunch of chips from your favorite vendor, and you paid a lot for parallelism and it still doesn't make your code run any faster, they'll send out application engineers, and this is exactly what they will do on site if you buy enough hardware from them. They'll do their performance profile, they're coded up with more threads, they're pretty good at it, it might actually run faster, it might not. And the basic problem with this is that there's lots of failures and lots of cases where within processors you actually run slower than with one, and here's a case. This is a real case. This is a problem in electronic design automation of doing routing, net routing, and this is a set of benchmarks. This is how fast you run on a single serial processor. This is how much worse you go as you try and multi-thread that application. Now, many people go, well, I don't see many published results like that. Is that really true? Well, if you get results like this, you don't get to publish them. That's why you don't see more of them, right? But anytime in an industrial audience that I present something like this, there's a lot of I know how that goes, right? Okay, and if we think, well, why is that? Well, in this process in which we're recoding with more threads and we're trying to access scarce resources, what's going on in our head is probably something like this, and these are all, real diagrams of how someone might reason about accessing some critical region with multiple processors. If it was left up to me, I'd use the one on the far right here, this UML sequence diagram, to try and think about it. And one of the faculty here in Corey, in E Division, Edward Lee, has written, I think, a great paper basically going through the problems with this way of thinking. But I think if any of you, and I guess you're doing some of this style of coding in this class, who sit around thinking about threads, locks, semaphores, data races, and so forth, know exactly the problem with this style of thinking. So what's the alternative? Well, I'm going to start out with some pieces of the solution that have kind of come together and then talk about how we put them together. So I was in industry for 15 years, and really I was not a software engineering zealot. I didn't have my own really killer ideas about how to do software. I just kind of grew up through an organization that ultimately we shipped 25 software products with over 20 million lines of code. And my pragmatic conclusion of that was that, robust pieces of software seem to have a really good software architecture, and that was much more important than the software environment which produced them. We didn't try and do any top-down, okay, you have to use this software environment, you have to code this way, and so forth. And the software environment, that is to say the total environment of debuggers, visualization tools, and so forth, were more important than any particular programming language usage. That is to say, it'd be great to say, well, once we started instituting the use of C++, those groups did much better than using C. Nah, it's simply not the case. Those who really understood how to architect their software and use tools in the environment effectively did much better than those, whether they were using C++ or C. So software architecture is pretty important. Now, one challenge I have is talking to student groups is, no offense, but unless you logged your first, say 150,000 lines of code or so, which some of you may have, some of you may not, you're kind of in the doghouse in the backyard era of software engineering where you kind of found some wood. You know, we were able to use some open source software and had some pretty minimal, you know, actually tacked up a diagram on your bulletin board of what you're doing, and didn't use too many tools, and kind of tacked it together, and you know, got that project, got an A in the project and the course and so forth, and that's kind of it. Where I think software engineering is today is kind of about the residential house. You know, it's not, you know, huge, and it's not so far, it's not incommensurable with a doghouse, but it does require a little more modeling, some sort of development process. It's not something that one person can individually do typically, and some power tools. Now I mentioned that we used to ship 25 products with 20 million lines of code. Well, that's bigger than a residential house, but what you know, to extend this analogy, I think what I'd say that we actually did was, it was more like a neighborhood. That is, if you look at any individual piece of code, at 1 million lines, we would try to restructure and figure out, you know, if it crept up towards 2 million, say, we really need to kind of refactor this and rethink how we're putting this code together. So it's not that we built some skyscraper, it's that we built residential neighborhoods of cooperating residential housing. Does that make sense? Yeah. Okay, and one of my favorite aspects that helped us with that is the notion of architectural styles. This goes back to this book with Shaw and Garland, or Garland and Shaw. And what they did is they codified a certain number of styles of taking software, identifying modules, and putting them together. And so I'll just throw the names at you. We'll talk about them more in just a bit. Pipe and filter, object-oriented approach as a broad approach of architecting software, layered, and so forth. And if I were to go back to the analogy, this is kind of like just saying, okay, someone wants us to build a residential house. Let's look at their requirements and let's just see, is it something pretty simple like a Cape Cod? Is it more like a bungalow? Is it something a little more exotic, which the, you know, details are much more important, like Victorian and so forth? So these architectural styles that Garland and Shaw came up with are kind of at that level. They're basic strategies for approaching how you modularize software. But that doesn't say that we don't want to ultimately be able to create entire skyscrapers, right? I mean, that is where we're going. But I also want to acknowledge where we are today. So I'll ask you this morning, how does the modularity that's afforded by a software architecture, how does that help in your software development? Take a stab. I know it's early, but I mean, you know, there's no magic answer here. You're all coders, you know. Yes, sir.
After a certain point, it's the only way to understand code.
So after a certain point, it's the only way to understand the code. Actually, that's worth recording here. Why don't you elaborate on that just a bit?
So what I was getting at there is, I know for myself, I can keep in my head somewhere between about 10 and 20,000 lines of code with some relative amount of detail. Anything beyond that, I start losing all of the details of how it works. And if there aren't really clean abstraction boundaries that I can think about at an abstract level without having to worry about sort of what's behind them, I can no longer understand what's going on in the code.
Sounds good. That's great. Other comments? About testing? Yeah. Yeah.
Well, yeah, okay, I'll talk about testing then. So, I mean, if you want to build something that you can add one more piece and test it, and add one more piece and test it, you know, making it so you only have an end-to-end test with no modular pieces makes it so that kind of, you can't pinpoint where the problem is.
Yeah, exactly. You can't pinpoint where the problem is. Great. So here's my kind of very much industrial perspective. You know, if I'm architecting a piece of software and I've got to be able to explain it to people, customers, to our own development organizations, do training and so forth, you know, being able to stand up and put the architecture on a single, you know, piece of paper or single PowerPoint slide is very helpful. As a project manager, you know, I'm managing maybe 7 people, and I need to be able to carve out meaningful pieces of the project to different people. If it's just one big monolithic piece of code or monolithic project, it's very hard to do that. Also, once I've dealt out those programming assignments to people, then I can track the progress. I can go in, at 11 o'clock at night, take a look and see, what's checked in, see what the current outstanding bug reports, how many regression tests are passed on each portion. And I can see, oh gosh, looks like one portion is kind of lagging behind. If I'm on the other hand an individual contributor, I'm doing my module or modules, and I'm able to focus on my module, without worrying about what everybody else is up to, right? That's pretty important. So, and finally, Modularity helps me identify key invariants for verification, and as we'll see, it also helps me to kind of look into what are the key computations. Now, I used to stop at this slide, and then some of my students said, all that sounds like kind of motherhood and apple pie. This is all great, but what's the real problem here? So what's life like without modularity? So think back on the largest project you ever did back before you kind of thought modularity was really necessary. What goes wrong there? Anybody care to share some hard-learned experience there?
Well, after a certain point, you just stop making forward progress. Because you can't understand what you wrote. You can't figure out where the bugs are. There's so many bugs in the software that you can't get around them to do useful work. Yeah, again, I think, thank you. I think that's a little bit like, in architecturally, if you just kind of tack a building together, it gets to a certain size and then starts falling apart under its own weight. It just can't seem to get bigger because there's always some weak link in the chain. So here's just a little potpourri. This is not some formal analysis, but so it's like spaghetti code. So if you've ever had the nightmare of having to maintain someone else's code that wasn't modularized, it's just, where do I begin? It's just one big tangle of spaghetti. You find yourself, because you're so, in a multi-person project, because you're so tightly coupled with everybody else, there's constant wars over the interpretation of the specification because there's no real decoupling your code from my code, right? Sometimes you're just, literally, you cannot progress in your piece of the code because it's so interlocked with another piece of the code that they've got to finish that portion. This is my least favorite thing. So, okay, you worked a little late. You're maybe 9 o'clock. You're driving home, feeling pretty good, checked in your code and so forth, and then just can't help but check the email one more time. 1 o'clock. This is back before we had smartphones, right? And your module's failing its regression test, or your portion of code is failing its regression test. How is it possible? I did the unit test, everything. My code looked really good. But because there's no real modularity between your code and the person in the cubicle that you were with, a couple rows down, when they checked in their code, they managed to effectively break your code, right? So it's hard to verify your code in isolation, therefore hard to optimize. This is a really, this course is a little bit more about performance programming, right? Parallel programming. So you may go, oh, well, this sounds like more kind of variants of kind of whatever the opposite of motherhood and apple pie is. But if you want to optimize your code, you have to make sure you're getting it right. And making sure that your code is right when you don't have modularity is actually very difficult. And of course, it's hard to parallelize without identifying the computations you want to parallelize. So this is, my advice is just don't go there. Emphasize modularity in software architecture from the beginning. Okay, so object-oriented programming is kind of the body of literature, the kind of the trend of research in software engineering that focused on this, focused on program modularity, data locality, architectural styles, and design patterns. But it kind of neglected anything about concerns with application concurrency, the computational details, a lot of focus on the modules, getting the modularity, not a lot of focus about what's in the module, and certainly parallel implementations were just outside of the scope of concern. So, to get at the point that I'm trying to sneak up on here, here's your pop quiz. David's taking attendance, so all those who didn't attend today will not get points. So we'll do this with a show of hands. Is a software program, not the process of building software, but the software as an artifact, is it more like a building or more like a factory? How many people think it's more like a building?
How many people think it's more like a factory? Well, that's a pretty shaky answer there. Come on, show your, okay, all right. So let's pass it on to someone who thought it was more like a building. Who would like to advocate? Okay.
I think it's more like a building because there's more of a layers on top that are kind of like the top layers rely on you having built the previous layers beforehand. And so because of that, that's why I thought it more like a building.
Sounds good to me. And more like a factory? Who would like to? Yeah.
The factory floor typically is fairly flat. It's not built everything on top of everything else. And there are a lot of pieces, kind of like, robotic assembly things that can be used for different things. You can kind of reshuffle them. And as long as all those things work, you don't necessarily have to worry about putting them all together, making it all work together as part of the same problem as building individual pieces.
So what I heard was there's modularity even on a flat factory floor, right? So what do buildings do? They kind of sit there, right? They shelter, they house, they protect. But what do factories do? They take input, they used warehoused or intermediate results, and they produce outputs. So with that, I'm kind of in the camp that says that software is a lot more like a factory. Does that make sense? And so where I'm headed here is that I think object-oriented programming, with all their wonderful building analogies, has done a great job of helping us think about this, but they haven't thought too much about the fact that software actually does something, right? So there's a key element missing here. So I claim, now a factory is also a building, right? It's a particular type of building, right? But a factory adds the element of you really need to think about the machinery. So what is the machinery of a software program? What's the analog of machinery? Go ahead, take a step. What's the fight?
I would say it's the manipulation of the data.
Manipulation of the data using computation, right?
Right.
I mean, yeah, okay.
Yeah.
Okay. So, computation sounds pretty important in software programming, and it's amazing when we teach software engineering here, I mean, we don't hardly say a word about computation. We might mention in passing algorithms are important and so forth, but if you want to know who really knows about computation, I think the high-performance computing community knows a lot about computations, concurrency, how do you do efficient programming and parallel implementations and so forth, right? And I think one high watermark of this was in the this lecture. It was just another trip that Phil Colella went up to talk to DARPA, probably to get some money, I would expect. And he talked about software requirements for scientific computing. And in this talk, he talked about 7 core, what he called algorithms, structured grids, unstructured grids, and so forth. And he saw that these are well-defined from a software standpoint, and that most of high-performance computing, if not all, could be done with these. Now, I'll point out immediately, these are not really algorithms, right? Dense linear algebra is not an algorithm. It's a family or class of computation, but definitely this is an important point, because this is on the track of, can we take this big ball of computation, this big ball of yarn of computation, and begin to kind of tease out particular types and threads from it? And so in the PAR lab, we spent a lot of time doing this, and ultimately the group of us all working together took those 7 dwarfs, as they called them, of high-performance computation and turned them into 13 sets of classes of computation that we thought covered pretty much all the applications we could find. So in this graph here, what we see is here are the computations we identified along the x-axis here at the top. The labels are on the right. We have 5 particular applications that we looked at that were fairly diverse. And then we also looked at entire classes of computations that had some sort of embodied literature. So the embassy benchmarks in embedded computing, spec benchmarks for quote-unquote general-purpose computing, databases, games, machine learning, high performance, and computer design of integrated circuits. Red means that something shows up a lot here. So dense matrix certainly shows up a lot in high-performance computing, much less in computer-aided design, much less in databases and so forth. Spec benchmarks seem to not have so much representation of dynamic programming and so forth. So red means it shows up a lot, orange here somewhat less so, green even less so, and then white or light blue as it appears to me here, even less. Okay, so again, well, what have we done here? We had a very organized way of attacking how we structure software. And I think starting with Phil Colella's work and through the Paralab, what we've tried to do is come up with a very organized way of how we actually organize and structure computation. Okay? So unfortunately, we can't just kind of go, well, looks like the high-performance computing community, they've got it pretty well all figured out. We can just kind of draft on their heels, because what they do is there's a lot of thought, put into the computation, and then if you ask them about structure, they're, typically kind of quizzical look. They kind of, in the architecture analogy, they kind of put a Quonset hut over it, And this is a small, computations get really big, but at the end, they use what they even have a name for it. It's called the monolithic architecture, right? So all those things that we complain about that go wrong when you try and just build bigger and bigger pieces of software without much modularity, I think all come home to roost in large pieces of high-performance computing software. Okay, so the question is, can we somehow integrate both these insights? The object-oriented community seem to really get at how to structure software. The high-performance computing community seem to get at how we organize our computations. Can we put these ideas together? So this is the approach that we're taking. Now, the first step is to identify, well, structure, program structure, and computations are kind of different, right? But we'd like to have them to be kind of the same type in a programming language sense, so that we can combine them in some way. So if we go back to those 7 dwarfs of computation, Phil called them algorithms, but they're really families of computations. And if we go back to those architectural styles, they're not really a formal, definition and architecture. They're really kind of almost an impressionistic set of architectural families, right? So the unifying concept that we chose to use here is the notion of a pattern, which goes back to Christopher Alexander's book for civil architecture, a pattern language. And he says a pattern just describes a problem which occurs over and over, and then describes a solution that you can reuse and reuse a solution without ever doing the same thing twice, right? So it's a generally applicable solution to a recurrent problem. That's in a nutshell. And then his pattern language book contains 253 different patterns which describe how you can design, going all the way from if we were to repopulate the bare earth and start putting cities and towns on it, all the way to very, very detailed architectural elements like a roof cap. And I had the great pleasure to spend an afternoon with Christopher Alexander a few years ago. He'd become something of a hero as I'd studied his book. And, sometimes these meetings are, if you've ever had these, are kind of anticlimactic. You kind of, wow, great work. You go up and talk to the person. They're kind of looking off in the distance, nodding their head, kind of like, who's this person? He actually, every single point on his pattern language that I engaged with him about, he was bursting with ideas. And he was I think he's a lot higher, frankly, on the computer science community and how we've integrated his ideas than actually the traditional civil architecture community that he was actually trying to address. Okay, so what good are patterns? First of all, pattern gives names and definitions to key elements of design. That's really important so that we can talk about things. When we're teaching, this is something we appreciate very much when we stand up and try and convey ideas. First of all, they give us new ideas. So those computational patterns get us thinking, wow, have I been thinking about this computation the right way? Those architectural styles go, oh, actually, I never really thought about organizing this software as agent and repository. Maybe that's something I should consider. So they give you new ideas, but equally importantly, they give you a set of finiteness, right? Which I think actually, at your stage of your career, one of these is as important as the other. It's a time to hear about new ideas, but it's also, when you're architecting some software, it's nice to know, I really only need to think about a fixed set of ways of structuring the software. Alternately, if I'm puzzled about what the core computations are in this application I'm trying to do, it's nice to know. Well, if you get through all 13 computational patterns and it's not any one of those, maybe you should look again, right? That should really give you a sufficient palette. They articulate design decisions succinctly, and they're very good at communication. So, you know, I asked for some spontaneous testimonials from David Sheffield here, or so forth, but you know, he's actually worked with some code in our group from previous people who use design patterns, and I think, you know, detailed program documentation is often too myopic. You know, a little, you know, one-page software architecture may be, you know, too high level. You know, as we go finer grain through this, sometimes you can zero right in on the piece of software that you want to address much more efficiently through the use of design patterns in the software architecture. When you go to implementation, these patterns embody a lot of experience about doing design. So if somebody stands up and they say, okay, I'm going to use agent repository for this, you know, you feel like you can use the full body of experience of people's use of that pattern, and you can predict sooner or later the repository will be a bottleneck. And people go, no, you don't understand these. The agents and the agent repository, those are very, you know, some of those are solving quite computational complex. Doesn't matter. May not be this year, may not be 5 years from now, but sooner or later, as the software matures, the repository will be the bottleneck. So they tell you the likely challenges that you're ultimately going to face in that software. Okay, so the approach that we are kind of championing in the Power Lab is to harvest the insights of object-oriented programming and identifying the software structure and the experiences of the high-performance computing community, as well as the kind of evolution of the Power Lab in identifying the key computations. And as we architect the software, we go back and forth between structure, computation, structure, and computation, and so forth, to come up with a full software architecture. So let me give you a little more detail on that. So at the highest level, we're looking at structure, computations. If you're like, deer in the headlights, I just don't know where to begin. I don't know, it all sounds so complicated, this application. You go, okay, well, why don't you just start talking about just write little tasks on a Post-it and just identify them, group them, see the order. Or maybe the data is where all the action is. Just identify where's the data sharing, how do the different tasks access it, and so forth. These are jogging your ways of thinking about how do you organize your software. So identifying the structure, again, we have a set list of common structural patterns represented kind of in little cartoons here. They say what our software is, the structure, how it's structured, but they don't describe how it's computed. Now, going back to our factory analogy, this is like the layout of the factory plant. The basic idea is, okay, think of my program as a factory, takes inputs, produces outputs. How do I want to lay it out, right? Then identify the key computations. Okay, these are the computational patterns we arrived at, and this is like the machinery. Okay, in this layout of the factory, what are the key computations that we do at each step? And then putting them together. So, you know, I just counted this morning, software engineering here 7 times over, I think, about 10 years, and I stood up and did the building analogy and showed Grady Booch's slides and talked about someday we'll build skyscrapers and so forth. And I never really questioned until we addressed parallelism, you know, that analogy, right? But the day that I went, you know, software is much more like a factory than a building, I literally rushed over to the engineering library and looked, you know, there must be some codified knowledge about how you build how do you create a factory? And what do they worry about? What are the chapters? There's things like scheduling, latency, throughput, workflow, workstation size. Workstation size is basically about how much machinery do you put in one place before it becomes unmanageable, which is analogous to what? Basic programming challenge we face every time we create a piece of software. Well, what would you say the analogy to workstation size is? Go ahead, pass it.
I mean, you can pick your favorite way of expressing this, but how much stuff to put in a function or a file.
Yeah, exactly. How big should functions be? That's a question we think about. Now, interesting that the people who figure out how you build an effective factory, they have ideas about that. They have experience, right? They have. So I was very pleased to see that exactly the problems that we were thinking about in terms of how to build large parallel software were the problems that people were thinking about when they were trying to put together a large factory. Okay, so again, looking at the same thing again. Here are structural patterns, here are computational patterns. We're going back and forth. What's the structure? What the layout? What's the machinery? What's the structure? What's the layout? What's the machinery? Back and forth. Or here's another analogy for you. Sometimes we think of these as like the atoms of computation, and these are the molecular bonds by which they get structured into more complex computations. Okay? Any questions so far? Do we have any on-the-spot, kind of conversion testimonials about you've seen the light now, or? Okay, all right. Yes, okay, we had down front here. Come on.
Okay, I have one. So I'm wondering, it's really cool that some of the questions you're thinking about were addressed from the literature on how to design factories, but how well do those ideas actually translate to, oh, here's the idea about how I should make my functions and so on?
Okay, so like some of these things, so I told you the good news. Now the bad news is, if you look at what in these books, the big paradigm for how they structure a factory plant is it's object-oriented programming. So it kind of pointed at, on the layout side, it pointed us back at ourselves. I think where they will really help us, and to a certain extent, Jim has already internalized this, or to a great extent, they talk about how to minimize the number, basically communication. How do you minimize taking things back and forth between workstations in the factory, right? So there you go. Basically minimize stuff. And I think the next step is the basic notion of how do you make sure that the results are very close to where they're needed. Now that's something, that's a little more general. That's not just data locality like you've got it all in memory somewhere, and how do you minimize how often you access it. It's how do you actually lay things out so that the results are very close to where they're needed. That's, probably several more doctoral dissertations, right? Jim, did you want to comment? Or?
Did the factories tell us anything we didn't already know then?
I do believe if we poured over that literature, I'm presenting all this as though it's a fait accompli, we've got it all figured out. We're still working this through, kind of application by application. So we haven't even taken really the big step back now that we've done a number of applications to say, okay, let's codify all that we've learned about architecting parallel software. So, and when we do, I think we'll want to dig more carefully into there and see what, yeah. But right now we're kind of doing the bottom-up case studies, right? Yeah.
Maybe one field that was motivated by factories was queuing theory.
Yeah,
and,
you bet.
And that's certainly something that applies to, scheduling jobs in our business too.
Right, right. Okay, so back to, remember, again, this is not a straw man. This, I would say, is the state of the art in parallelizing software, and this is what you have to do. You have to spend a lot of time about how do you decompose computation in threads, and then how do they communicate and compete for sparse resources. And what we're proposing is an alternative in which the same person, rather than thinking about all that, is basically thinking top-down, what are the computations that I want to do, and what's the structure. And all that may seem like just the kind of thing you'd expect to see at 9:30 a.m. in a academic classroom, some toy examples or so forth, some completely unrealistic way of designing software. But I'm going to show you today how we actually apply this. Okay, but first I know you're reasonably familiar with the computational patterns already. I want to give you more detail on structural patterns. Okay, so here's an inventory of them. Here's 10 that we use. The vocabulary, just so we share a vocabulary about it, is we talk about the components of a structural pattern is where the computation happens. So they're literally kind of little black boxes initially of where the computation is going to happen. The connectors are where the communication between these happen. And then configuration is how you put the components and the connectors together, okay, in a hierarchical manner. Okay, so our first and most commonly used pattern is for structure is pipe and filter. And who's got an example? Jim, do you have the microphone? Oh, here we go. No. Who wants to answer? Pipe and filter. That's not a tough one. Pipe and filter.
I mean, one trivial
speak like that. No.
Sorry. One trivial example of this is sort of using pipes in Linux to communicate between processes. You can put together an entire string of independent things to process data.
Right. So yeah, pipes are you know in a Unix computation are a standard example. Although it's really let's use an example of a monolithic piece of code that if you peek inside is actually structured in this way.
You can use the same analogy inside of a program, right? So you can look at, you know, an obvious case is stuff with image processing and computer vision, where you have a series of transformations you apply to your data, and eventually you want a number to pop out at the end.
That sounds good. That sounds like a good one. This is, you know, basically a pipe and filter. So again, these are the filters, these are the pipes, and an image retrieval system, compiler, logic optimizer. These are, again, pipes going through filters. As a matter of fact, if you talk about a piece of software over, say, 30,000 lines of code at the top level, and you don't end up drawing a pipe and filter initially at the top level, then I'll be really surprised. Because there's also almost always processing the input, writing the output, some hard stuff in the middle, more details there, so forth. Okay, iterator pattern. So what's the iterator pattern? We have some initialization condition. We can do things pretty much in any order that we like, or maybe we can have very loose scheduling precedences between them in the middle of this block, and then we kind of synchronize at the very end, and then we go, well, did we meet some exit condition? If so, we're done. Otherwise, let's go through and iterate. So how about some examples of this? Now, my rule in class is if you're looking at your laptop, you have to answer. Okay? If you're so familiar, you don't need to pay attention to the lecture. Then you. Yes, sir. Particle method? Particle method doesn't jump out at me. I mean, there's no IEOR students in here today, early in the morning. I mean, there's a whole large body of computations which kind of fall into this, which are folks in the IEOR building. A big step.
So, I mean, what pops out to me here is like an iterative solver that's converging to a solution.
Exactly. Iterative solver converging towards solution, right? So almost any optimization problem will have this basic example. So, you know, in the quadratic optimization portion of a support vector machine software, we're updating, we're kind of building a fence in n space across the feature vectors. We update the surface. We see if we have outliers that are too far away from the surface. If so, we know we need to iterate to improve the surface so that no outliers are above our error condition, right? It's basically an optimization problem. Okay, MapReduce. Okay, so some people think that Google invented MapReduce. It actually goes back to early Lisp programming, and where you had a simple thing where you could map a function on to discrete pieces of data, so that notice there's no overlap in the data, and then we reduce down the answer. So examples of MapReduce. Don't be shy. Map reduce. Yes, sir. Passing back to the microphone.
Maybe trying to trying to count the occurrences of the number of words, number of times each word occurs in a large body of.
Yes. So we have discrete sets of words here. Let's say web pages. We map the count for those, the count function onto those, and then we reduce down to get a final count. It's pretty very standard approach used in kind of cluster level or data center level computing. How about a finer grain solution, kind of software you might do in this class? Any ideas? Any examples?
I mean, it's sort of linear algebra style stuff, not directly linear algebra, like sort of rank one update kind of things where you just want to add something to a matrix.
Yeah, anytime so if you look at that support vector machine computation I just showed you, within that, how do we determine what the outliers are? We have a whole bunch of inner products and subtractions to perform, right? Those are all independent and discrete. We can do them all, map that function out. It's a very small dense linear algebra function, and then reduce back to collect any outliers that are outside the error condition, right? Okay, another important pattern, agent and repository. This goes back to early work on artificial intelligence and speech recognition in particular. So at the core of it all is the notion of a repository or blackboard, in other words, a database. You have a bunch of agents that will act on the blackboard, and the way I like to think about it is literally as though we have the blackboard here. Imagine we're all agents. We have, say, a problem we all want to solve. And the way that we solve it is agents come along, they do a portion, then they put the pen down. Other agents come along, they may erase a little, they may rewrite a little, and so forth. They put the pen down. And so they're all operating on this common repository that is the blackboard. And when you're done, what's the result? The result is just whatever is on the blackboard when you're done. That's it. Right? So that's the basic notion. Now, in this, back to the classroom analogy, there needs to be a manager because if everybody's running forward and grabbing the pen and so forth, that doesn't work, or one person's erasing while the other person's writing and so forth, that can be, so you need a manager to orchestrate that. So, examples of this. For the first time we have notion of really persistent data and the action all being about the data, not the yes, sir. You on the microphone? Okay.
Well, this is kind of obvious, but just any kind of key value store where you have clients in a database and the clients are trying to interact with it, and you want to know what data is left at the end.
So, yeah, if you, again, I think as I followed that, I think one distinction I'd like to make is, remember, whatever the result is, it's left here. So it's not like the agents come out and they report, they query the database and they report, okay, here are the number of key value pairs of this variety. But, so I'm not sure I fully understood I'm sure there's a breadth of application of the example you gave, but just want to make sure. The key thing to remember about this is whatever we do, it's left in here at the end. Okay. Compiler. This is the first thing that comes to my mind is we have an internal program representation. We have a battery of optimizations that we perform over this. The order in which we perform these is for some people kind of a secret sauce, and it can be iterative. And one can imagine even organizing the internal representation so that multiple of these could be done on different program segments simultaneously. And a related thing, this is logic optimization. So for me, the problems of compiling, say, C down to produce object code or compiling Verilog down to produce a circuit are very related. So you can do the same thing on a circuit. So this is our circuit database. These are a bunch of different optimization agents acting on it simultaneously. And the result is just the circuit that's left in the database. Okay, just another one here, the process control. So this brings up a certain point. This is in process control, we have a set of control parameters that affect a controller. A controller has a set of manipulated variables that activate the actuators. The actuators actually act on the process. There may be other input variables to the process. We have some sensors on the outside and some control variables. And the notion is that this is kind of streaming. Data comes in. Actually, data comes in through here and kind of streams through continuously. Right? Now, visually, if it hasn't occurred to you so far, maybe think a little bit, what structural pattern does this look like that we've already seen? Just visually. Just don't be afraid of the obvious answer.
So both pipe and filter and iterative.
Yeah. It's this looks like iterative, and the whole thing looks awfully like pipe and filter. So this is why patterns, both computational and structural, are more kind of human ways of organizing things than they are strict formalisms, right? And I struggled to try and convey this all the way going back to my software engineering CS267 days, and I finally find the right analogy, which is, some of you may not have faced the joys of home ownership, but you know, if you've got some plumbing to do, you're really glad you have a pipe wrench. Somebody comes along and goes, couldn't you do that with this crescent wrench? Well, kind of arguably a pipe wrench is a kind of crescent wrench, right? Looks just a little bit different, but if you have to do some plumbing, you're really glad you have a pipe wrench. If you have to do exactly process control here, you're really glad you have process control and are not trying to just kind of handcraft it out of pipe and filter. Now we could do this out of pipe and filter, but remember, a lot of what patterning gives us is vocabulary. So you'll see people working on a process control kind of application going, well, wait a minute, in the controller, okay? In the control, the minute you say that, you know exactly the portion of the architecture you're talking about. When we actuate the process, okay, there's a vocabulary that travels with this that's very valuable. So Jim, you had a comment?
So just by analogy, when we talked about sparse matrices and structured grids and unstructured grids, there was a lot in common there too, and depending on the application, you might use any one of them.
Yeah, exactly, and that's why I think patterns is a good way of thinking about the, you know, what are those 7 to 13 dwarfs? I think they're patterns. They're just general ways that humans organize information. They're not algorithms. They're not strict mathematical definitions, or I don't know that you could come up with a strict mathematical definition for the, I mean, just as you say, between structured versus unstructured. It's a little bit of a human process about when you shift from one to the other. Okay, examples of this. The first hint is that we have one in our classroom. No, not sitting in a chair. Go ahead. Yeah. Yeah, so the video camera that's doing the filming here is a good example of process control. There's an even more standard example of right about over there, the rheostat for the thermostat, so forth. So again, the obvious examples are things like where we really have like a temperature sensor, thermostat. Somewhere in here there's a furnace or air conditioner producing hot or cold air and so forth, and then we have this continuous sensing, right? But this pattern is really useful in a lot of computational context here. So if you take something like, this is again, one I showed you a few slides ago, this circuit optimizer with a lot of timing optimizations, and you can kind of think of this as we're looking at, is the circuit fast enough? And if it's not, then we look at the user timing constraints, and the controller then launches a set of transformations to actuate against the circuit, to modify it. Then we're kind of simultaneously actually measuring the speed of the circuit and launching, identifying our next set of transformations, and then actually modifying the circuit. Now, I talked about my hard-learned lessons of software management. This is a perfect example, which is using this architecture, each one of these major steps is very complicated. The analyzer, which actually analyzes the speed of the circuit, that's hundreds of thousands of lines of code. When I'm writing that code, I don't want to be thinking about anything other than I have a circuit and I'm trying to analyze the time. The control, which is given the current state of the circuit, what next transformations do I want to launch? That's also very complicated, right? So that is not hundreds of thousands of lines of code, but it's very smart code. It's very sophisticated code. Any transformation which optimizes a circuit, that's in the tens of thousands of lines of code, and it's pretty algorithmically intensive. Now, what this architecture allows me to do is none of those people have to talk to each other very much. These people confirm that they have a circuit. These people say, I just get some information about the circuit, and I look in my recipe book for what we should do next, and then I write my code presuming that I've got the circuit all to myself, and I show up, I modify it, and I leave, right? And none of these have to interact with each other. Okay, last one, puppeteer pattern. Yeah.
Do you get a race condition or maybe a serial bottleneck because of that architecture you just described? Yeah, so this whole question of, and maybe it's worth mentioning, I think when we first started talking about these in the Parlab, I think for Kathy, look, this was all a big snooze, right? Because none of this tells you very much about parallelism. So as a matter of fact, in this architecture, as Jim is saying, the very way we structure it here has some kind of serial dependencies in it, right? But in some sense, the problem natively has some serial dependencies. But what it does do is, when you go through this and you look more carefully at it, to a certain extent, the fact that this is so serial shows, if I can back up, yeah, didn't have to go far, that if we want parallelism, we've got to look somewhere else. So each one of those is one of these process controls, and they operate very coarse-grained maximum, say, four independent processes. So if I want massive parallelism, well, I've got a big circuit, tens of millions of instances. So I can chop that up in the database and have these relatively serial programs operate on that in parallel. Okay, so sometimes knowing that the parallelism isn't here, helps you to understand, I better find it somewhere else. I claim that if you just take someone off the street or out of a little group, building a logic timing optimization will say, well, why don't you parallelize it? This is not the architecture they will come up with. They will immediately jump in to each one of these, and it'll be some time of trying to tease threads out of that before they realize, there just is not a lot of parallelism here, right? Okay, last structural pattern I want to treat today is puppeteer. Do we have many people from up the hill and so forth, scientific applications people in our august audience this very morning? Okay, well, the basic notion here is we have a series of puppets which are kind of in their own computational universe, is the way I would think. They have their own way of thinking about the problem, they have their own way of structuring the data, they have their own preferences. And yet, as things evolved, maybe they were developed entirely independently as though they were standalone program, but then over time we realized, oh gosh, we want to put them together to do a more complex application. So the puppeteer takes the individual puppets and basically manages the scheduling between them and how they exchange data. Now, what's the difference between this and agent and repository? The puppets have their own data universes. There's no central repository here. As a matter of fact, we're choosing this architecture because we can't afford to keep taking all the data out of the puppet, restructuring it, put it in a form that Puppet 2 understands, then Puppet 2 reports back, putting the applicant instruction that Puppet 1 understands. That'll all be too time intensive. We're hoping that we've structured, these puppets are naturally structured so that they have to share modest amounts of data, but they do need to be scheduled and they do need some data exchange. Okay, so examples of this architecture? No, Jim. We must have some scientific computing types here. This is, as I understand it, where they spend most of their life. Yeah, and I'm going to pass it back. David, it's time.
I think that most, like, large-scale parallelized quantum chemistry and solid-state physics programs work this way.
Do you want to elaborate a little more?
Yeah, so there's sort of a central, like, main controller process that essentially hands out a lot of work to all of the child processes. The child processes solve some sort of subset of the problem, and there is some interaction between all of the puppets, but it's been minimized as much as
Now, are the
possible.
puppets all doing basically the same thing on different data?
For some applications, yes.
In those applications, I'd say that's actually more like MapReduce as far as it is from the data cluster style. So let me give you some examples which come to my mind. So one is video game. So at least in the video games that we've kind of taken apart and put back together, the physics engine, the graphics engine, and the AI engine all have basically different ways of looking at the world that have to be put back together here. And so this is a natural architecture for that. And then this is one of the Parlab applications. And this is, I think, a really good, first of all, this is I haven't kind of coerced this into our representation, but this is how they were thinking about the problem. You have this big monolithic code which simulates blood vessels. Everybody's all happy about that, doctoral dissertations, years of work, and so forth. And then you have this big body of code that simulates simulation of blood and blood flow. And then that was developed in isolation, and this has its data representation because that's appropriate for vessels, and this has this data representation which is appropriate for blood. And those are very different representations. The last thing you'd want to do is embark on a project which somehow does some grand unification of those two, because experience has shown those projects usually fail. So what you build instead is a data broker interface that is the puppeteer, with each of these as puppets. And then the data broker does two things. Number one, it schedules, because blood flow varies much faster than blood vessels. So you do that scheduling. And then you need to pass some data back and forth. As the vessel changes, that changes the dynamic of blood flow. As the blood flow changes, say, with a heartbeat, that changes the structure of the blood vessel. Okay? Jim, did you want to comment?
Not on that one.
Okay. Great. Is this example pretty clear? Yeah. Great.
Oh.
Okay. Yeah.
And one more example that we'll hear about in a later guest lecture is climate modeling. You have the ocean, you have the atmosphere, you have other parts glued together this way.
Right, right. Yeah, as a matter of fact, I had a student in a seminar class do basically going up the hill, and I think she found, 17 different examples, all of which have this basic structure. And the first indication is, these people were in blood vessel land, these people were in blood flow land, different lands apparently, and yet one day people wake up and, boy, wouldn't it be great if we put these together? And this is a natural way to think about how you put them together. Question up front here? Yeah.
So the question I had was sort of one of definition. If you have a data exchange layer where it's not responsible for the control, it's just sort of transformation of data, would you consider that a puppeteer or not?
Sure. So the puppeteer does two things: schedules and manages data. If all it's saying is you two run along and just asynchronous tell me when you've got something to tell me, it's still controlling, right?
So what if, say, puppeteer 1 is in control and there's a data exchange layer where sort of it has to translate into something the other puppeteers know?
Why don't you use the microphone, sir?
Sorry. So I don't have a concrete example here, but the case I'm wondering about is, say, the control logic actually lives in one of the puppets. And
For the whole system?
For the whole system. And it doesn't directly know how sort of the data formats of the other puppets work, but it's the one deciding what to do, and all of the sort of puppeteer here is doing is handling the data exchange and sort of doing the transformation between the different formats.
Right.
Would you?
Well, one of the, so it's a great question, right? I mean, that's one can easily imagine that. So let's I don't know how correct this will be the example, but let's suppose these two groups get together and the blood simulation. People say, look, we've got 250,000 lines of code. You've got 30 lines of code. We've got this all figured out. You should just do what we tell you to do. And so, yeah, fine, we'll have a little data broker interface, but we'll actually do the scheduling inside the blood flow, because that's where really most of the action is. We have a much finer time step, and we can say every so often, every 20 time steps or so, okay, why don't you see how the blood vessel is actually perturbed. Pragmatic solution, bad architectural decision, right? Because when you're messing around with the blood flow, you want to be kind of not thinking about how am I scheduling the blood vessel, right? This pattern developed by Damon Rowson, who at Sandia Labs, was out of his pragmatic experience of saying, when these things come together, there's a myriad of ad hoc solutions that people use to put these together, and most of them go wrong, right? And what you want to do is you do want to isolate the scheduling and the data exchange in one place, because this code is going to evolve, and this code is going to evolve, and the last thing you want is some summer intern coming along in your blood simulation, right, and having some great ideas about how to do that, and then suddenly, because that intern doesn't know that this code is included in a whole other application, suddenly the schedule of the blood vessel changes and the people's results don't work. So you'd like to really keep the schedule and the data exchange in a place where you can keep an eye on it. But this, once as I say, I'm just not by nature a software engineering zealot, right? But once you kind of get this pragmatism down, you're ready for a whole lifetime of, but wait, won't it be so much more efficient, basically, in parenthesis, this week, if we do it this way? And then you go, I can see why you'd say that, but in 5 years from now, I can tell you, despite the fact that we think this code won't still be around, it will be, and it'll be, really smart. We'll be thinking it's really smart. Someone will be going, wow, what a good idea that they put all that right where we can see it. We can see where the schedule is. We can see the data exchange right before our eyes. Yeah. Okay, detail on the computational patterns. That's what you do day in, day out. You explore these every class, so I'm not going to go in more detail on that. But what I want to finish up here is with a real, it's a high-level example, but it's a real example of architecting an application. The application I'm going to talk about is speech recognition. You have a voice input. There's a bunch of DSP-like signal processing you do, which breaks it down to speech features. Up here you have a language model, which is all the smarts of whatever language you're dealing with. And then you have an inference engine, which takes this language model and the stream of speech features you get and turns that into word sequences. And this basic system architecture, notice I didn't call it a software architecture, the system architecture has been very, very effective. So here is the high-level software architecture that we came up with when we parallelized this. So you see we've kind of, just for space sake, to emphasize this inference engine, we've got the voice input, the feature extractor over here. Language model's a big deal, but we're not emphasizing that. And then here's the actual inference engine, which figures out what you're actually recognizing, okay? So let's go through the architecture of this. So at the top level, previous was a system diagram. Now these are actually pieces of code. So we're going to call that a pipe and filter architecture, which this is one big filter at the top level. Inside of that, then we look at the computations. What we're really doing, Michael Jordan would come in here and say, well, you're doing graphical modeling there. But if you look at the actual computation and how we compute it, we're using dynamic programming, right? So now that monolithic dynamic programming has a number of steps, which are kind of initially shown here. And so inside of this dynamic programming, we implement that with a pipe and filter. We have these filters here. And inside of each filter, there's a MapReduce, and then there's a basic iterative refinement loop here. That's the top level architecture. Any questions so far?
So in this case, the computational pattern, which is dynamic programming, has inside of it structural patterns. Is that how you implement it?
Good. Yeah, I guess I didn't emphasize that much before, but when I talked about going back and forth between computational and structural patterns, any significant computational pattern will have to have some modular structure to compute it, and will be broken down to smaller level computations, right, as we'll see. Okay, so here's the core of what occurs inside here. So let's spend some time on this. And sorry, it's a bit of a busy slide, but here's the pure mathematics of it, which is we're trying to determine the next state based on the frontier, the current probability of the previous states, and the likelihood due to the observation. So looking at that graphically here, we, based on a series of observations, gotten to a certain level of this frontier of probable states. Kind of think of these as partial prefixes of speech that we've recognized. We've got a new observation, and determining what the next frontier is a product of what's the probability that we're in this state, what's the probability that when you're in this state you go to this state based on the language model, and what's the probability that if you see this observation that you go to the state. We compute that over all viable next states, and then we take the max of those, and that updates the frontier. Okay, so we want to parallelize this. How do we architect that? So going back to the prior diagram, we have this outer iterator. So this is progressing the frontier. We have inside this pipe and filter where we gather the operand. We do this probability calculation for the current states. We do this maximum probability for the next states. So let's go in that in a little more detail. Gathering operands is basically, it's a MapReduce, although it's really just a data movement. There's no real computation. We're just getting all the operands together in one place. Okay, all you parallel programmers out there, why are we doing that? Oh, one second.
Maybe to make it easier to reuse data?
Data reuse or data locality, right? I mean, if we have to go chasing pointers around while we're trying to do a parallelism, we're not going to get much done. So we get all the operands together, coalesce them. Remember, we're going to use this on a SPMD machine, so we're going to be able to get all the data in one place and then just crank right through it. Okay, so then for this one, the current probability, this is just a Gaussian mixture model probability, which again can be computed in just basically a MapReduce style, right? We fit these Gaussians and then we reduce it down to the best fit. And then in terms of the next step in the frontier, we're trying to compute, what's the maximum probabilities among all the different places we might go seeing this next observation. What are those that have a maximal probability? So we take these portions of the computation, map them, and then reduce down to a set of maxes. Okay, just to be clear, rather than saying a single max, I should use sense maxes above a certain threshold. Okay, because we don't want to pin down at this point to a single state. We're trying to keep a frontier with states. Okay, and that's it. So I showed you the iterative refinement, the pipe and filter, and we saw 3 different MapReduces here, and through that iteration, that produces the software architecture. And this is the basic idea of how it works. So above we have the observations. So these are what are called phones. I wanted for a long time to call them phonemes. But phones are just raw sounds independent of language. Put them in a language model. So there's like a recognize speech, okay, little 10 millisecond slices. And then we have some candidates here. It could be recognize speech or recognize speech, right? So using the algorithm I just showed you, we iterate through progressing the frontier till we get to the end. And
find based on our language model that recognized speech is a more likely candidate. Okay? So, that's real work. What I have here are a set of applications that we've really done. So maybe let's stop here, going back a little bit. At this point, I think if I was in your chair going, yep, it's another one of those guest lectures, somebody has a wacky idea, they come in, never been proven in, they did a toy program once, and now they're declaring victory and writing a bunch of papers about it. I think that'd be a fair assessment. But we kept trying this out. These are a set of applications that we did. These are the speed-ups that we got. My friends at Intel always get a little anxious when we talk about speed-ups. What does that mean? Means that the people using the code before got normalized to 1, and then they used our software and it went 100 times faster. Now there's lots of details of architecture and was there any MATLAB code in there that ran slow and so forth. But applications people are very interesting. You come in, you make their code run 100 times faster. They don't ask those questions. How did you get that? So they take it and run, right? So even though architectural people want to know, oh yes, but did you turn on the SSE optimization here? And so, okay, the application people just say, yeah, I want to use that code now. That's it. Okay, so that's what I'm emphasizing here. So we got lots of good speed ups. What I just showed you was the speech recognition. Now, if you look at it in this group, you go, whoa, that's kind of the dog of the group, right? I mean, 11x speed up compared to all these 100x and so forth. And I have to say, 4 years ago, 3 years ago, we're a little, well, try harder and so forth. Well, it turns out speech, because of all that chasing pointers around and so forth, and then you finally, progressive frontier, and then you want to write the next state, but everybody's contending to get to the next state. It's very hard to parallelize this. So we actually, this is arguably among our most successful of all these because this has been so hard to parallelize. But as you see, I think we've had a lot of good success across a range of applications. These are the, I can honestly say top tier conferences that we've been able to publish in and show impact. So what I'm trying to say, it's a long way to say anything, that I think this really works. And I think as much as, sometimes when people show, well, here's all these good results, well, that's impressive. Of course, there were twice as many that didn't work, but I can honestly say there isn't anything that we've attacked here with this methodology that we haven't been able to get significant speed-ups on. Okay? And a couple of these are software you can download. So these have both been, this is, in addition to its 2,900 downloads, I think it's the winner in citations now at 190 different citations in the last 4 years. So we academics loved, it's like baseball cards. We talk about how many citations we have. And, Okay, so summarizing, our basic approach has been start with a cool application, identify the overall software structure, identify the key computations, and then compose these down to yield a software architecture for the application. What I've shown you today, if you go back to that Christopher Alexander slide, I talked about a pattern language. So the difference between patterns and a pattern language is typically a kind of a layered approach to doing a full application. For Christopher Alexander, this was a whole building or a whole shopping center or a whole university campus. For us, it's a whole application. I showed you the top level of it, but there are these other levels of our pattern language, which I didn't emphasize today. About those top levels, so what about the computational patterns? When I was in school, computation was kind of like the Greeks when they talked about, there was just matter, right? It was like all matter was kind of the same. Computation was kind of computation. You took algorithms, but, there were graph algorithms, things like that. But I mean, between the very detail, the algorithm you're dealing with, and the broad set of computation, I didn't really have a taxonomy in my head. These computational patterns help us to kind of break down, there are just different types of computation. And Alan Kay has this quote that I love that basically the right point of view is worth 100 IQ points. And what I find, honestly, is when I'm talking to algorithms people, like I spent an afternoon with Chris Leiserson talking about algorithms and so forth,
this framework of being able to break down applications into these computations makes me feel really smart. It makes me feel, even as someone, Chris Fleischman, is such an encyclopedic command of variety of algorithms, that I'm looking at things at a different granularity. He talks about computational finance, and I just see, oh, Monte Carlo around a dense linear algebra computation. That gives me a certain power. He's going into the details of the particular computational finance algorithms that he knows, but I find my perspective of, no, it's just Monte Carlo wrapped around dense linear algebra, gives me some power. It makes me feel like I have more insight into that class of applications. So these make me feel smarter. These make me feel organized. As a former software manager, these structural patterns are what I want, so that when I drive home, the feeling that what's going to happen between when I left the office and when I get home, nothing too bad can happen. Maybe one module is going to blow up. That doesn't mean the whole architecture is going to go down, right? That the impact is so. From my object-oriented experience through these parallel applications, any complex application can be broken down into these manageable modules. Okay, so this is the total pattern language. Again, I've just shown you the top level today. These are the computational patterns. These are the structural patterns. And then the remainder of this is all codified in a book with Tim Mattson, who's worked from Intel, who's worked a lot with this. And once you go through this organization into these high-level patterns, Tim's book basically tells you here's a strategy you can use for parallelizing it, then implementing the software, then running it on parallel hardware. Okay, so summary. I think software architecture is the key to any type of good programming, in particular parallel programming. Structural patterns help us to enforce modularity, expose invariance, and parallelism. I showed you 5. With 5 more patterns, you've got all you need to do all the software you're ever going to write. Computational patterns help us to get into the machinery of what needs to be parallelized. And the orchestration of these two, the structural and the computational patterns, allows us to create the architectures. If you want to get up to date, it's kind of pretty primitive looking website. We're trying to improve that, but there's a lot of information there about the patterns. And then if you want to look at some of our publications on applications we've done, you can find it there. Okay, with 1 minute to spare, any questions?
So when you described your successes with the applications, presumably it didn't work the first time. You said there were several iterations. So what changed? Did you change which structural patterns you used, or what did that iterative process look like?
Yeah, that's a really, I would say there were some applications where, the speech, we really didn't change too much through the whole history. So I don't know whether we just got lucky. I know that Henry Gabb, when he came from Intel, we went through the architecture of his application in an afternoon. And then about midway through the implementation, he tossed that out and went with a different. This is a debate that Tim Mattson and I have a lot about whether when we're doing the high-level architecture, pipe and filter and all that stuff, do we really need to be thinking deeply about the final parallel implementation? And I think Henry's experience shows, well, if you have 2 equally serviceable software architectures, the one which accentuates the kind of problems you'll anticipate in the parallel implementation is the one that's ultimately going to help you the most, right? So the good news is that, remember I said Henry and I spent an afternoon. It's not like we spent 3 months and then, 3 months later he had to throw all that away and throw 6 months of effort, and then he spent another 3 months. It's like, 6 weeks in the effort, he scrapped that afternoon of work, re-architected it on his own in an afternoon, and then went with that. And then also the architecture, remember, it's breaking things down into modules. So the agents and an agent and repository approach may turn into your puppets and your puppeteer approach, right? So often it's not the leaf computations that you change, it's the overall structure. Yeah.
So how did Henry know that the first one was wrong?
So probably you've heard about as much detail on that as I did, but trying to do
again, I think it's less that it was wrong and more about, let's get away, you know, there's a way, I mean, you can kind of look at, sometimes we talk about pattern mining. So you're digging in and find pattern. So sometimes, you know, if you think of structural patterns as kind of looking at the geology in a particular way, it's one way of looking at geology, but it doesn't show where the gold is, right? And so when he restructured it, and I'm trying to think of exactly, but I think it was something like an agent repository kind of thing. When he restructured it, it really showed clear where the key opportunities for parallelism were. So, you know, maybe just in this lecture you brought up before about this process control. Like the process control, if we'd featured that more and the repository less, you could look at process control for the rest of your life and the timing optimization, and you just never find enough parallelism. If you then kind of highlighted more, no, think of it as an agent repository of which there are many process control agents going on. Oh, now I see where the parallelism is. So I think it's more that kind of thing. Okie dokie. Well, thank you.